Yes,
Yes,
ma'am.
yes, ma'am. Okay, fine. Yeah. So it's recording. Okay. So yeah, in week 5, we studied about linear transformations, right?
Yes, sir. Yes,
Yeah.
ma'am.
So week 6 is a continuation of linear transformations. Um, yeah. So what is a linear transformation? Maybe we'll quickly recall that and then uh, go ahead. What is a linear transformation? Can someone quickly tell me?
Ma'am, it is a function which maps an element from a vector space to another element
Hmm.
uh, in a separate vector space, and it respects the two operations,
Yeah.
the addition and the scalar multiplication.
Right. So a linear transformation, we usually use the alphabet T to denote a linear transformation. So a linear transformation is nothing but a function between two vector spaces that satisfies two conditions. Yeah, it respects the operations of addition and scalar multiplication of the vector spaces. So T of V1 plus V2 is equal to T of V1 plus T of V2, and the second condition is that T of alpha V1 is equal to alpha times T of V1. So sometimes we use the bracket, sometimes we don't use the bracket. Like if I write T V1, it's nothing but T of V1. Both of these denote the same. So yeah, if these two conditions are satisfied, then a function between two vector spaces is called a linear transformation. So now what this basically does is you have V and W, two vector spaces, and then you have a function between them. You have V1 and V2 in the vector space. V1 gets mapped to some value, say T of V1, and then V2 gets mapped to T of V2. So if it's a linear transformation, what happens to T of V1 plus V2? Why should V1 plus V2 be in V?
Because it's a vector space.
It's a
Right.
vector space.
Yes, it's a vector space, so it is closed under addition. So V1 plus V2 belongs to V. So where does this gets mapped to? It gets mapped to T of V1 plus T of V2. That's it. And similarly, alpha times V1. Alpha times V1 gets mapped to alpha times T of V1. If all this is satisfied, if these two conditions are satisfied, then it is a linear transformation. Fine.
Madam,
Um,
could you please expand that? For me, it is displaying very small.
is it? Uh, is my screen small to everyone? Maybe you should pin my thing. Is it big enough for the others?
You can go full screen even.
Yes, ma'am.
Yes, ma'am, it's fine.
Full screen.
How do I do full screen? Is it this? No. Hmm. What about this?
Zoom it, ma'am. Enough.
Better, ma'am. Something better.
Yeah. Okay. So this is a linear transformation. Okay. Is uh, is this a linear transformation? I am talking about T from R2 to R2 defined as T of x comma y is equal to x plus y comma 3x plus 1. Is this a linear transformation?
No, madam.
Why not?
Because one is done.
Huh.
0 is
So,
not full.
yeah,
T of 0.
T of 0 comma 0 is 0 comma 1. We know that if T is a linear transformation, then T of 0 should go to 0. 0 should go to 0 if T is a linear transformation. So because 0 doesn't go to 0, T is not a linear transformation for this function. Or if you want, you can even check for the addition condition. If you take say T of 1 comma 1 plus T of 2 comma 1, what is T of 1 comma 1 for this mapping?
2,4.
2 comma
2
4.
comma 7.
2 comma
Sorry,
3x,
2
3
comma
plus
2,4.
1.
4. 2
4.
comma
4.
plus t of 2 comma 1 is 3 comma
3,
7.
7.
3,7.
So this is 5 plus 5 comma 11. What is t of 1 comma 1 plus 2 comma 1? T of 3 comma 2, what is this?
5 comma
5 and
5
7.
comma
7.
10, no?
10, yeah.
10.
Yeah. So, yeah, these two are
Yeah.
not equal, and because of this, it is not a linear transformation. Fine. So, yeah, obviously, by now you would have known that a linear transformation cannot have constants, right? Because the constant will get added twice if that is the case, right? Right? So you won't have terms like this. Are you allowed to have t from R2 to R defined as t of x comma y is equal to x squared? Is this a linear transformation?
No, madam.
Why not?
The power is
Because
2.
Yeah.
power should be linear. Only
Yeah,
one.
it's a linear transformation, so it should all have powers. One x squared is going to create a problem because as simple as that, t of minus 1 comma minus 1 is going to be 1. It is not equal to minus times t of 1 comma 1, right?
So, madam, sorry, actually, I didn't understood that first one. T of 0, how it will be 0. Sorry for that.
You want the proof?
No. How it will be? Could you please, yeah, T of 0 comma 0, how it will be 0, 0, 1?
Oh, this one. That's
Yes,
because I'm substituting x is equal to 0, y is equal to 0 in the function.
0. Yeah,
Huh.
0.
So
So it
0
will
plus
be,
0.
oh, no, yeah. Sorry, sir. Yeah, got it. Yeah, thank you.
So that is how
Yeah.
this one is equal. Right. And yeah. Then what else? So a linear transformation cannot have powers. So basically, a linear transformation from Rn to Rm is going to look like T of x1, x2, xn is equal to a1 x1 plus b1 x2 plus etc. plus okay, ABC is not nice. What do we do? A11 x1 plus A12 x2 plus A1m xn, A1n xn, comma A21 x1 plus A22 x2 plus A2n xn. Like this, I'm going to have m components, right? Because it's an Rm. am1x1 plus am2x2 plus etc. plus amnxn, right? A linear transformation is going to look like this from Rn to Rm, right?
Yes, ma'am.
Yeah. So if I look for say R2 to R3, P of x comma y is going to look something like, or let's keep it R2 to R2, a1x plus b1y comma a2x plus b2y. This is how a linear transformation is going to look like. Yeah, just by looking at the function, if we want to check whether it is a linear transformation or not, then this is how it's going to look like.
Ma'am, could you show us the example of R2 to R3?
A mapping or in the general form?
Yeah,
In the general form, it's going to have just one more component.
no, by
A3x
example, I
plus.
mean with real numbers.
Oh, okay, fine. So say I'm taking R2 to R3 defined as T of x comma y is equal to x plus y 2x 3y. Fine?
Okay, thanks.
Yeah. Okay. So this is what a linear transformation is. Okay. What else do we know about linear transformations?
0 goes to 0 first.
0 goes to 0. What else? What
T
else
of
in week 5?
x plus y is equal to
Yeah, that is the definition of a linear transformation. And then, is there anything else in week 5 that I'm missing?
scalar multiplication.
Yeah, that comes in the definition. Okay, I guess then we'll just proceed. Yeah, I think we'll just proceed. What is a one-to-one map? When you have a function, you talk about a function being one-to-one, a function being on to and all that, right? One-to-one function. What is a one-to-one function?
One input to one output, ma'am.
So, what did you say? One
Input should have one output. I mean,
one input
matches.
will have only one output, but two inputs cannot go to the same output, right?
Yeah, that's what. Each and every input has its own
A
output.
unique output.
Ah.
Yeah, right. Fine. So this is a one-to-one map. A map that goes to unique outputs is a one-to-one map. So obviously, one function, one variable cannot go to two different outputs, right? One input cannot go to two different inputs. Then it is not even a function. But other than that, every input should go to a unique output. So this is not a one-to-one map because this one and this one, two inputs are going to the same output. So this is not a one-to-one map. For it to be a one-to-one map, every input should go to a unique output. So how do we represent this mathematically? How do we represent a one-to-one map mathematically?
F of V1 is equal to F of V2.
So f of x is equal to f of y should imply x is equal to y. Yeah. So if the images of 2 points are the same, then the 2 points have to be the same. The 2 inputs have to be the same, right? Yes, this is what a one-to-one map is, right?
Yes, madam.
Yeah. So the same holds for a linear transformation also. One-to-one linear transformation. So a linear transformation is said to be one-to-one. If T of V1 is equal to T of V2, then V1 should be equal to V2. So you will assume this, you will prove this. If you can prove it, it is a one-to-one map. If you cannot prove, it is not a one-to-one map, right? Yes?
Yes.
Okay, ma'am.
Fine. But because it is a linear transformation, I can do something much more simpler than this. So this one, I have T of V1 is equal to T of V2. I'm assuming this, right? Assume T of V1 is equal to T of V2. So I'll bring everything to one side. T of V1 minus T of V2 is equal to 0. What can you tell about T of V1 minus T of V2? Can you simplify it and write it as T of something?
T of V1 minus V2.
Right, perfect. So you can write this as T of V1 minus V2 is equal to 0. Fine. So I can write it like this. This is my left hand side. And then I want to prove V1 is equal to V2. So V1 minus V2 is equal to 0. Right?
Yes, madam.
So whenever T of V1 minus V2 is equal to 0, I want to prove that T of V1 minus V2 is equal to 0. Agree?
Yes.
Yes, ma'am.
Yeah. Can I replace this V1 minus V2 with some other vector, say just V? Put V is equal to V1 minus V2. Then I'll get T of V is equal to 0 implies V is equal to 0. Agree?
Yes, ma'am.
Then can you please repeat?
Yeah. So I am just rewriting this statement into something else.
Okay.
Fine. So T of V1 is equal to, is this clear that this is what you should prove for a one-to-one map?
Yes, madam, it is clear, but what you write after V is equal to V1 minus V2?
I'm just rewriting the left-hand side first, in the sense that I'm assuming T of V1 is equal to T of V2. I'm writing it as T of V1 minus T of V2 is equal to 0. That's nothing but T of V1 minus V2 is equal to 0. Is this part clear?
Yes, ma'am.
Okay, madam.
Here I'm writing it as V1 is equal to V2. That I can write it as V1 minus V2 is equal to 0, right?
Okay, madam.
So what should I prove? T of V1 minus V2 is equal to 0. implies V1 is equal to V2. That's what I should prove, right? This is the part that I assume, and this is the part that I have to prove, right?
Yes, yes.
In case
So
if
instead of
V1, ma'am, in case
V1
if
minus V2, I'm
vice
just putting a
versa.
V. That's all.
Ma'am, can I ask you a question?
Yeah, sure.
So in case if V1 is already given as V2, so will the reverse be proved? Can it hold for the otherwise or other case also?
No. For 1-to-1, you have to prove only this implication, right? Not the other
Okay.
way around. Only
Okay.
this implication you have to prove.
Okay.
Yeah.
Fine.
You'll assume this and then you'll prove this. So is it clear why we have to? It is enough if I prove this for a linear transformation. For a general mapping, you cannot do this, right? This getting converted into this is because it is a linear transformation, right?
Yes, ma'am.
Yeah. So for what are you actually checking for a 1-to-1 mapping? You will pick a point and then you will look at the set of all pre-images of that point, right? You'll pick a point in the codomain and look at how many pre-images it has, right?
Right.
If it has exactly one pre-image, if
Then it
every
is
point
mapping.
has exactly one pre-image, it is a 1-to-1 map, right?
Right.
At most one pre-image. There may be points which don't have a pre-image also, right?
Yeah.
Yeah. So that's exactly what you're doing here. But if it is a linear transformation, then you needn't check for every point in the codomain. It is enough if you check the pre-images of only the zero vector. So if you have a linear transformation, you look at the pre-images of the zero vector. There's going to be a zero vector in the codomain, right?
Yes, sir.
Because it's a vector space. So you look at the pre-images of the zero vector. If the pre-image of the zero vector is only the zero vector, then it is a 1-to-1 map. Where does the zero vector of the vector space V go to under any linear transformation?
To the zero vector in the function.
Yeah. So the zero vector, we know, already goes to the zero vector. 0 gets mapped to 0. Is there any other point that gets mapped to 0? That is the question. If there is any other point that gets mapped to 0, then obviously the map is not 1-to-1, right?
Right.
Yeah. If 0 is the only vector that gets mapped to 0, that is whenever T of V is 0, if the V from the domain has to be 0, then it is a 1-to-1 map. Else it is not 1-to-1. Is it clear?
Yes, ma'am.
Yeah.
Yes, madam.
So let's pick a linear transformation, say T from R3 to R3. T of x comma y comma z is equal to 3x, 2x plus y, 3z, okay, 3z minus 2y plus x. So now if I want to check whether this is a linear, this is a 1-to-1 map or not, obviously this is a linear transformation, right? Nothing to check. Yeah.
Yes, madam.
Is it 1-to-1? How will I check?
We will substitute the function with 3x, y, and z values as 0, 0, 0 everywhere. And if the output is 0, then the function is 1-to-1.
Yeah. So you will start with T of x comma y comma z is equal to 0 comma 0 comma 0. If you can prove that x comma y comma z is equal to 0 comma 0 comma 0, then you are done. It is a 1-to-1 map, right?
Yes.
If this is not happening, then it is not a 1-to-1 map. Right. So what is T of, this is what we are assuming. This is what we want to prove. Okay. So what is T of x comma y comma z?
Will
3 into 0
3 into 0, comma 2
No,
into
why
0.
3 into 0?
because x, y, z are 0, no, ma'am. 0,
No,
0, 0.
no. I have to prove that. I want to check whether that's happening or not. So you should forget this part for now.
Okay.
We're just assuming t of x comma y comma z is 0, 0, 0. What is t of x comma y comma z?
Okay.
3x comma 2x plus y
Y.
comma 3z minus 2y plus x is equal to 0, 0, 0. When will two vectors be equal?
The
Now
corresponding
take
3 x is equal to 0 then.
3x.
corresponding coordinates are equal.
Yeah, corresponding coordinates are equal. So you'll do
So y
this.
is equal to 0.
Yeah. So from here you'll
X
get
and
x
y
is
0.
equal to
So
0.
z also 0.
Here you'll get y 0. Here you'll get z 0. So do I get x comma y comma z is equal to 0?
Yes, madam.
Yes.
So is this map 1 to 1?
Yes, it is 1 to 1.
Yes.
So this is a 1 to 1 map. So you see that the 0, 0, 0 vector has exactly one pre-image, that is 0, 0, 0 itself. So this is a 1 to 1 map. Okay, so now what about R3 to say
Yes.
R2? T of
Excuse me,
x.
madam.
Huh.
If
Yes.
codomain is rather than R2 to R4, then will it one-to-one function or not, madam?
We'll check that. We'll check
Okay,
the
okay.
properties. Yeah. Okay. So now suppose this is the map. T from R3 to R2. So how will I check whether it is 1 to 1? What is the first thing I will assume?
T of x comma
0,
y.
0.
X plus y is equal to 0.
So you will be assuming T of x comma y comma z is equal to 0 comma 0. Is it clear why only two components?
Because it
Yes,
is R2,
because
ma'am.
Yeah, because it's R2. Perfect. So x plus y comma y minus z is equal to 0 comma 0. So this gives me x plus y is equal to 0. Y minus z is equal to 0. So what do I get from here?
X is equal to minus y.
Minus.
And
Y is equal to z.
okay, so I get x is equal to minus y is equal to minus z, right?
yes, madam.
Does this guarantee that x comma y comma z is equal to 0?
No.
No, madam.
So can you see that this map is not 1 to 1?
Yes,
Can
madam.
you
I
give
can
me
say.
one more pre-image of 0? Can you give me some x comma y comma z that goes to 0 comma 0 other than the 0 0 0 vector?
1 minus 1 minus 1.
Right. So you actually know how the vectors should be, right? If t of x comma y comma z is 0, then x comma y comma z is going to be satisfying this condition. What is t of 1 comma minus 1 comma 0 minus 1? What is x plus y?
1 minus 1.
0.
0.
And 0.
0.
Yeah. So you see that there is another vector other than the 0 vector that goes to 0 comma 0, right?
Yeah. Yes.
Yes, ma'am.
Yeah.
And dimension is less than domain dimension, then it is not a.
We'll get to that. But yeah, for that you need something more. So we'll get to that. But is this clear that this is not a 1 to 1 map?
Yes.
Could you please repeat that?
Okay. So is it clear till this? Is it clear how we got this?
Yeah.
Yes,
We are
madam.
equating the terms like what we did for the last equation and how this we got, right?
Yeah. And then is it clear that this does not guarantee that x, y, and z should be 0?
Yes, ma'am.
I can put x is equal to 1. In that case, y will be minus 1, z will be minus 1, right?
Yes.
So, ma'am, we can write the same thing as 2 minus 2 minus 2, any number, with any number.
Yeah. Okay. What is t of, same map, what is t of 3 comma minus 3 comma minus 3?
Yeah, same 3, 0 comma 0. Okay.
Yeah. So there are so many vectors that goes to 0, 0, 0, right?
Yes, ma'am.
So it's not a 1 to 1 map. Is that clear?
Okay. Oh, yes, clear, ma'am.
Yeah. So yeah, let's come to that dimension part a little later. Now we'll just stick to this 1 to 1 thing. Okay. So yeah, suppose I have R2 to R3. T of x comma y is equal to x comma y plus x comma 2y minus x, something like this. Is this map 1 to 1? How do we check?
Q of xy is equal to 0, 0. Check.
T of xy is 0, 0 or 0, 0, 0?
R2 to R3 0,
So 0 comma 0?
comma 0.
Yeah. T of x comma y is in R3, right?
Right.
Yes, madam. R3. So 0, 0, 0.
So I'll get x comma y plus x comma 2y minus x is equal to 0, 0, 0. So what do we get from here?
X is equal to 0.
Huh.
Y plus x is equal to 0. That's why. So y is also 0.
Yeah. And then the last condition is not needed. We already got x is equal to 0, y is
Yes.
equal to 0. Yeah. So you did get x comma y is equal to 0 comma 0. So is this map 1 to 1?
Yes.
Yeah. So we started with T of v is equal to 0 and we ended up with v is equal to 0. So it is a 1 to 1 map. So is the definition of a 1 to 1 map clear? And how do we check whether it is 1 to 1 or not? Is all this clear?
Yes, ma'am.
Yes, madam.
Yes, ma'am.
Okay, fine. So are there any doubts in any activity questions that you want to ask? Or if you haven't gone through the activity questions, no problem. You can ask later in the next session also. So shall we proceed?
Yes, ma'am.
Yes, madam.
Okay. So for 1 to 1 map, what are we checking? We're checking for the pre-images of 0 in W. Right?
Yes,
If it
madam.
is only 0, then it is called a 1 to 1 map. If it is not equal to the singleton set 0, then it is not 1 to 1. Right? Yes?
Yes, madam.
Yeah. So this set is nothing but the kernel of a linear transformation. So the kernel of T is nothing but the pre-images of the 0 vector. So it is the set of all vectors that gets mapped to the 0 vector. So you have a domain and a codomain, and then you have a linear transformation. You're looking at the set of all pre-images of the 0 vector. Where does the pre-images of the 0 vector lie?
In the kernel.
The domain.
In the domain.
Domain.
It's a subset of the domain. Right. Can you give me one vector that you know for sure is there in the kernel?
0 vector.
Zero vector.
The 0 vector always belongs to the kernel. Can you show that this is a subspace?
Yes, ma'am. 0 vector is there.
What are the other conditions you will check?
Multiplication and scalar closure.
You'll check whether it is closed under addition and closed under scalar multiplication.
Yes, ma'am.
So how will you check closed under addition?
0 plus 0 equal to 0.
No.
We'll
That's
take
not
V1 and V2 in kernel of T.
Let V1 and V2 belong to kernel of T. Then what do we know about V1 and V2?
T of V1 is equal to 0.
And
T of V2 is equal to 0.
What should I check?
T of
V1 plus V2.
Yeah. I want to check whether V1 plus V2 belongs to the kernel or not. That is whether T of V1 plus V2 is equal to 0 or not. How do I know that this is 0?
Because T it's equal to T of V1 plus T of V2.
Right.
And both are 0.
We already know these two are 0. So T of V1 plus V2 is equal to 0. So this is true. Is this clear?
Yes. Done now.
Can you similarly check alpha times V1? Does
Yes,
alpha times V1 belong to the kernel? What is it that you have to check?
T of
T
alpha
of alpha times V1 is equal to 0.
Yeah, you want to check this. How will I get this?
we can get
Alpha T of V1.
Alpha V1 is equal to 0.
I know that alpha T of alpha V1 is equal to alpha times T of V1. And I know V1 belongs to the kernel, which means that T of V1 is 0. So this gives me 0, which means this is satisfied. So the kernel of T is a subspace of the domain V, W, T is a mapping. You have the kernel here. And that's nothing but the set of all pre-images of the 0 vector. Is it clear?
So for one to one, there will be one kernel, is it?
No, not one kernel, but you're right. Means what you're thinking is correct, but the way you're telling is not right. Tell me, what is it exactly?
This one to one.
One kernel means what? It means I understood what you are thinking.
One vector means
there'll be exactly one vector in the kernel.
Okay, yeah.
Does everyone agree to this?
Cardinality of kernel is 1.
Yeah.
Yes, madam.
So specifically,
have a
cardinality of kernel will be only 1 in case of one-to-one function.
Yeah. Otherwise, it's a subspace, no? There are infinitely many vectors, right?
Right.
Yeah. So is it clear to everyone that if I have a one-to-one map, I know that the 0 vector has exactly one pre-image, and that pre-image I know, right?
Yes.
Yeah. So is this sentence clear? It's an if and only statement.
When you say that we know the pre-image, so does that mean that we know that what is coming back as a pre-image to the kernel and what is exactly the function? That's what it means?
No. I know one pre-image of the 0 vector. Can you give me one pre-image of the 0 vector?
0?
It will go to 0 only.
Yes, ma'am. 0 only.
You shouldn't say it will go to 0. 0 will come to
It
this.
comes from.
Yeah, it comes from 0. Okay.
T of 0 is 0. So I always know that 0 belongs to the kernel of T.
Right.
In the sense that the 0 vector is always a pre-image of the 0 vector.
Got it now.
Yeah. So I know one element in the kernel. If that is the only element, then the mapping is 1 to 1. Agreed?
Yes, ma'am. Agree.
Yes.
Okay. So maybe let's find the kernel of the above mappings. Can you quickly tell me what is the kernel of this linear transformation? Let's call this T1. Can you tell me what the kernel of this linear transformation is?
0, 0, 0.
0, 0, 0.
Yeah. So one-to-one map, no? We have already shown it is a one-to-one map. So it's enough if I just find, if it's a one-to-one map, what will the kernel be?
0 vector.
Yeah. So one-to-one map we have already shown. So the kernel, I'm representing that with T1. So the kernel is nothing but 0, 0, 0. Right? What do we know about, let's call this T2. What do we know about T2, the kernel of T2?
Images.
0, 0. Ma'am?
Did we show it is 1 to 1?
Oh, no.
No, ma'am.
Madam, it is not a 1 to 1, so we cannot say about kernel.
We know for sure that the kernel is not 0.
It will have all the pre-images.
Yeah, it is a subspace, that we know, but it is not 0, 0. Let's find out what that is. Okay, we'll do that. What about T3? What is the kernel of T3?
is 0, 0, 0.
0, 0, 0.
0, 0,
This
0.
is a one-to-one map. So the kernel of T3 is also what is it, 0, 0, 0 or 0, 0? T3 domain is R2, so it is 0, 0. Fine. So let's go back to T2. T2 is x plus y, y minus z. T2 is R3 to R2. T of x comma y comma z is x plus y comma y minus z. So how am I going to find the kernel? How am I going to find the kernel? Someone?
X plus y equal to
X
0.
plus y equal to
Right, this is right. So T of x comma y comma z is equal to 0. That's what I want to find out, right? I want to look at all those x, y, z that go to 0, 0, 0, right?
Yes, yes.
Okay, I shouldn't have written it like this.
It's 0, 0 only, no, ma'am?
Oh, yeah, sorry. Yeah. Set of all x comma y comma z in R3 satisfying T of x comma y comma z is equal to 0, 0. Agree?
Yes.
Yeah. So how will I do this? I'll write it the same way. X comma y comma z in R3 satisfying. What is T of x comma y comma z?
X plus y, comma,
X plus
y
y
minus z.
Y minus z is
This is equal
0,
to
0.
0. So it is the set of all x comma y comma z in R3 satisfying x plus y is equal to 0 and y minus z is equal to 0. Going on from here, you know how to find the subspace, basis and all that, right?
Yes, ma'am.
Yeah. So what is this subspace? What do we get from here? We already calculated, right? X is equal to minus y is equal to minus z. Agree?
Yes, madam.
So what is this subspace?
X comma minus x comma minus x.
Y comma minus z. Minus
X comma minus x comma minus x.
minus x.
Where x can be anything, right?
Yes, ma'am.
Can you give me a basis for this?
We can pull out of that
1,
x
1
outside.
minus 1.
1 minus 1 minus 1.
Kernel of T2, 1 minus 1 minus 1. So what is the dimension of the kernel?
1.
1.
1.
Yeah. Dimension of kernel of T2 is 1. And the dimension of the kernel of any subspace is called the nullity. Dimension of kernel of any linear transformation is called the nullity. I said subspace, right? So I know that the kernel is always a subspace, and I know that I can find the dimension of a subspace, right? So the dimension of the kernel is called the nullity of the linear transformation. Is it clear till here?
Okay, so from here, this equation, if the nullity is 1, we can substitute in rank plus nullity theorem and find out the rest of the things, right?
Yeah. So tell me, what is the nullity of this linear transformation?
1.
0.
Okay, this one.
0,
0,
ma'am.
ma'am.
Why 0? We just found out, no? 1.
Yeah, it's 1. X is equal to minus, x is equal to minus.
So the dimension of the kernel is 1, right? There is one element in the basis, right? Yes?
Yes, ma'am.
T2 you're asking, ma'am. Yes.
This problem.
1-to-1
Oh,
transformation is 0.
yes. It's 1 only.
Yeah. What is the nullity of T1 and T3?
That is
0,
0, no, ma'am.
Yeah.
Yes.
So T is 1-to-1 if and only if kernel of
Nullity
T is 0, right?
Yes, ma'am.
This is equivalent to nullity being 0, right?
0. Yes, ma'am.
If and only if nullity of T is equal to 0. Is this
Ma'am, is
clear?
this being live streamed on YouTube?
No, the streaming had an issue. It said that some participant is there because of which streaming cannot happen.
Ma'am, so will a recording be made available after this?
Yeah. Once the recording is processed and available on the drive, we will upload it on YouTube.
Okay, ma'am.
So, ma'am, in case of
I think last session is not uploaded. I think.
No, it is uploaded.
Everything is there.
It is there. The only thing is confusing is because one of the video is there which is of only few minutes, so that's why it's confusing. But there's one more video available of the same date.
Oh, okay. Then I'll make sure that the old one is deleted, the smaller one.
Actually, that is creating a confusion because that is only of 1 minute or 2 minutes, something like.
Oh, okay.
Only 10 seconds, I think.
Yeah, 10 seconds.
Yeah, usually this streaming starts, but then it says that someone is there because of which the streaming cannot happen and it stops.
Ma'am, I have a question here.
Can
I ask? So whenever T is 1 to 1, we say nullity is 0 since the kernel is 0. So here, whenever 1 to 1 function is there, it would be a full rank. So rank will be equal to dimension, right?
Dimension of the codomain, yes.
Yeah. Okay.
So is it clear to everyone what is a one-to-one map? What is the kernel of a linear transformation and what is nullity of a linear transformation?
Yes.
Is all that clear?
Yes, ma'am.
Yes, ma'am.
Anyone has any doubts? You can ask, and then we'll proceed to on to.
Ma'am, is the kernel of the transformation same as solution space of the transformation, ma'am?
Solution space means what? You want a matrix, right, for solution space? But yeah, that's a good connection. Solution space means you want a matrix, right? System of linear equations, right?
Yes, ma'am. The solution should be 0. Your transformation is 0.
No. We saw a transformation which is not 0, but the kernel is 0, no? One-to-one map. Here, this one. Right? This transformation is not 0, no? What is the 0 transformation? When do you say a transformation is 0?
When the output is 0, ma'am.
Output of every vector is 0. This is the 0 transformation. What is the kernel for this 0 transformation?
0 only, no?
No, think and tell me. You have V, you have W.
Yes, V itself, ma'am.
It's the domain.
Complete V
The
itself.
entire space, right? Every vector goes to 0.
Yes, ma'am.
So in this case, can this map be 1-to-1?
No, ma'am.
Obviously not. Every vector is going to the 0 vector. Fine. So the kernel of this linear transformation is the entire domain space. Right?
Is there any specific function or name for this wherein everything what we put the value of V it is going to 0?
This is called the 0 map, the 0 transformation.
Okay.
What about the identity transformation? What is identity transformation? What is the identity transformation?
Every element maps to itself, ma'am.
Right. So the domain and codomain has to be the same first of all, right?
Yes, ma'am.
T of V is equal to V. This is the identity linear transformation. What is the kernel of this transformation?
0.
I. Why is it 0?
Because 0 alone maps to 0.
Perfect. 0 is the only vector that goes to 0, right?
Yes, ma'am.
So here the dimension of this kernel is 1 when it is only 0 vector. So there is something in the dimensions. Can we say it is
No.
dimension is
Dimension is 0. Can you give a basis when the 0 for the 0 space?
No, we cannot give.
Because there is no linearly independent set, right? That will generate this space. So the dimension of the 0 vector space is taken to be 0.
So in this case, what's the nullity, ma'am?
Here nullity is 0, right?
Nullity is
0
0.
vector
Rank
space.
is
0. Oh, 0. Yes.
What is the nullity here?
dimension of vector
Dimension
space.
of V, ma'am.
Perfect. Whatever is the domain, the dimension of the domain will be the nullity here. So is it clear?
And could you please take an example here?
Okay. For what? Example of
For
what?
wherein every vector is getting mapped to 0.
It is this, no? This is the mapping, no? Every vector is getting mapped to 0.
Yeah.
You
In
just
terms
put P
of
is equal to R2, W is equal to R3 or something. And map every vector to 0, that's all. T from R2 to R3 defined as T of x comma y is equal to 0 comma 0 comma 0. That's all.
okay, ma'am.
Yeah.
Ma'am, have you explained how to check if a linear transformation is onto yet? I've
No,
joined a bit late.
I haven't come to onto yet. I'm just going to start. So do we just take a 2 minutes break for you all to digest what has happened till now?
Yeah.
Yes, we'll go through that, ma'am. Yes, ma'am.
Yeah, just a quick recap of what is a one-to-one map.
Yes, ma'am.
We have a linear transformation, which is a function between two vector spaces satisfying these two conditions. A one-to-one map means every input has a unique output. That's exactly what we are doing here also. But being a linear transformation, the only advantage that we have is instead of checking for every vector, we will just check for the 0 vector. We'll look at the pre-images of the 0 vector. T of V is equal to 0 implies V is equal to 0. If this happens, then it is a one-to-one mapping. And then how do we check one-to-one map? You will assume T of V is equal to 0. If you can prove V is equal to 0, it is a one-to-one map. And yeah, so basically to check whether a map is one-to-one or not, you're looking at the pre-images of the 0 vector. If it is the singleton set 0, then it is a one-to-one map. If it is not the singleton set 0, then it is not one-to-one. The set of all pre-images of the 0 vector is called the kernel of the linear transformation, which is this. Set of all V in the domain such that T of V is equal to 0. If the kernel is singleton 0, then it is a one-to-one map. If it is not singleton 0, it is not a one-to-one map. And because the kernel is a subspace, we can talk about its dimension. The dimension of the kernel. The dimension of the kernel. The dimension of the kernel is called the nullity of the linear transformation. So this is the final conclusion. T is one-to-one if and only if the kernel is 0, if and only if the nullity is 0. Is it clear?
Ma'am, I have a doubt
Yes,
in
madam.
linear transformations.
Yes.
Ma'am, what would be its geometrical implication?
So it's a function between two vector spaces. So what does a transformation do? So say for example, I have T from R2 to R2, where T of x comma y is equal to, just give me 1 second, let me construct an example. Okay, let's keep it simple. 2x comma 2y. Suppose this is my linear transformation. This is a linear transformation, right?
Yes, ma'am.
Yeah. So I have the domain, which is R2, and then I have the codomain, which is also R2. What happens to any point x comma y? Where does it go to?
Scaled up by 2, right?
Yeah. Just going to 2x comma 2y, right?
Yes, ma'am.
Yeah. So if I look at what happens to this square, the unit square, then I can tell that under this linear transformation is going to become a square of side 2, side length 2.
Yes, ma'am.
Yeah. If say I had a rectangle, if I had a rectangle of length 1 and height 2, what is it called? Length into breadth. Breadth 2 and height 1. What? Length is 1, breadth is 2. Then I'm going to get a rectangle whose length is 2 and breadth is 4. Right?
Yeah, ma'am.
So geometrically, I can see where do shapes get transformed into, right? Given any shape in the domain, I can tell you what is the output shape that I'm going to get. And because it is a linear transformation, the shape is not going to move anywhere, right? From where it starts, it's either going to become big or it's going to become small. The shape is not going to change and it's not going to get shifted elsewhere, right?
But that's because the dimensions are the same, right?
No, not because the dimensions are the same. Will a rectangle like this get shifted to a rectangle like this?
No.
Never. If this is going to happen, it means that the function has some constant, right? Say x plus y plus c, comma x plus d. When something like this happens, when that plus c and plus d is there, that is what makes this shifting happen, right? Translation.
Yes, ma'am.
And the shape is going to change if if I'm going to have some x squared, y squared terms and all that, right?
Yes, ma'am.
Yeah. So the shape is also being preserved, and it's only going to become smaller or bigger in size. That's all.
Ma'am, is x square comma y square a linear transformation?
Why don't you tell me whether it is a linear transformation or not? First of all, when we talk about a linear transformation, we want a domain and a codomain and the definition of the mapping. Okay, let us assume this is what you were asking. Can this be a linear transformation?
It should be closed
No.
under addition and scalar multiplication.
No, ma'am.
It cannot.
Will it be closed under addition and scalar multiplication?
No.
Why
No,
not?
ma'am. Yes.
-1 + 1.
We get same image for -1, -1 and 1, 1.
So what? That doesn't say that this is not a linear transformation, right? That
Yes.
says that this is not an onto a 1-1 map. It doesn't say that it is a linear transformation.
When that is square.
When the square term is there, what is the problem?
We want linear, so like.
Right. Yeah, but what is the condition that is getting violated?
Not closed
So
under
it's not closed under addition.
Not, ma'am.
not closed under multiplication.
No. What is closed?
That means one value of x when we are putting it is giving me two values. It can be for two values of x we are getting the output x square.
No. So
No.
what?
We have
That
to
doesn't
take two
mean-
elements, ma'am, and then we have to perform addition.
Right. So you take two elements, x1, y1
X2, Y2.
and x2, y2. And then you see what happens to T of this.
Yes,
If
ma'am.
you get it is equal to this,
T of x1 plus T of x2, y2.
if it is
Then it is
equal to
closed.
this, then it is a linear transformation. It is not a linear transformation. What is T of x1, y1 plus x2, y2?
x1 square, y1
x1
square.
plus x2, comma y1 plus y2.
x1 plus x2, y1 plus y2. This is
x1 plus x2 whole square.
whole square plus y1 plus y2 whole square.
It's comma, ma'am.
Oh, yeah.
It's
Sorry.
comma. Yes, ma'am. Yes, ma'am.
So I'll get x1 squared plus x2
squared
squared plus
2x1
2x1 x2, comma y1 squared plus y2 squared plus 2y1 y2.
Yes, ma'am.
What about this portion?
That is x1 square.
That will be x1 square plus y1 square
Y1
only.
square.
Plus x2 squared, no? Okay.
Yeah.
It's
Yeah,
going to be
x1
x1
squared,
squared,
comma,
y1
yes,
squared
plus
x2 squared, comma y2 squared. So you see that this term is extra.
Yes, ma'am.
So these two will not be equal even if one of x1, both of x1 and x2 are not equal to 0, right? If any one of them is equal to 0, then these two will be equal, right?
Yes, ma'am.
But otherwise, it's not going to be equal.
And could you please repeat the last thing? What you said? Which one of the two has to be 0? X1 or X1, X2
No,
has to
will
be
this
0
be
or...
equal to this?
No, it won't be
You
equal.
agree it's not equal because of these extra terms, right?
Right, right.
But suppose x1 is 0. Then this term will go missing, right?
Right.
Yeah, but then you shouldn't check just for certain values, right? This should be true for all values.
Right, right.
Yeah. So you can say pick like t of 1 comma 1 plus 2 comma 2. Check what happens to this. This is not going to be equal to t of 1 comma 1 plus t of 2 comma 2. Right? That is why it is not a linear transformation. Not because it has more than one pre-images or things like that. It's definitely not an onto function, but it is not even a linear transformation. Can I look at this as just a function instead of a linear transformation? Just some function, right?
Yes.
Yeah. But if I want to look at it as a linear transformation, it is not a linear transformation. Even as a function, this is not one-to-one. Anyway, we are talking about linear transformation. So first, it's not even a linear transformation. Only then we look at whether it is one-to-one or not, right?
So in general, in case if we want to say that whenever the degree is, because we have already proved it here, so whenever we have x squared terms, x cubed terms, so it will never be a linear transformation.
Yes,
Rightly, we
because
can
you're going
reject
to have that extra terms that come out of the expansion.
Ma'am?
Yeah.
So the conclusion is that it is not closed under addition, ma'am.
No, you don't say this is not closed under addition. Closed under addition means you pick two elements from the set, you add them, whether it belongs to that set. That thing is only called closed under addition. This condition is not called closed under addition. You get my point?
Yes, ma'am.
Yeah, when I say v1 comma v2 belongs to v, this implies v1 plus v2 belongs to v. This is called closed under addition, not this.
This is the condition for the transformation, ma'am.
Which one? This is
The
one of
above
the
one.
conditions
The above
for
one. Yes,
transformation.
ma'am.
Yeah. So the transformation should respect the addition of the vector space.
Oh, yes, ma'am.
It should be compatible with the addition and
Scalar multiplication.
Scalar multiplication.
Scalar multiplication.
Yeah, it should respect those operations.
Ma'am, this is pretty clear. But then in the previous thing, when we were discussing that you put any, we can put any value of x comma y, and when if we can scroll up, so it is getting mapped to 0. So I'm not able to visualize that. How is it possible that we put any value and the output is going to be 0?
Which one? Here is it? This one?
Yeah. So for any value of v, the function is going to get us 0. So is there any practical, is it practically possible that we put any value of x and y, it is going to give us 0?
Yeah. So this is my R2. So say this map is from R2 to R3. My output is always going to be this. The entire R2 gets mapped to this single point. This is a function, right? Why not? Right?
I'm not convinced yet. I am not able to visualize that. How can it be possible that you put any value of x and y, it is going to get to 0? So this is a very imaginary kind of function then.
Yeah. But you agree that this is a function? It's of no use to us. That's a different thing.
Yeah.
Every vector is getting killed by this linear transformation, basically.
Right.
Yeah.
Got it.
Okay. So, yeah, is the one-to-one map clear? What is kernel of a linear transformation? What is nullity of a linear transformation? All that is clear?
Yes, ma'am.
Yeah, okay. I'll just take a quick break. I just want to drink some water and my bottle is empty. I'll just take a 2 minutes break.
Yes, ma'am.
Yeah. Yes, I'm back. So I hope one-to-one map is clear to everyone, right?
Yes.
Yes, ma'am.
Yeah. Okay. What is an onto map? What is an onto function? When do you say a function is onto? When do you say a function is
When
onto?
codomain is equal to range.
Perfect. You have some function from say x to y. So you say that the map is onto if the range is equal to the codomain. What is the range of a function?
All the output values.
Yeah.
Yes,
It is the
images.
set of all outputs. So if this is equal to the codomain, then it is an onto map. Right? And how do we represent it mathematically? How do we represent
So
onto map?
we say that when a
Range.
function v is mapped to w is onto, if every w belongs to w and there exists maybe f of v is equal to w, maybe function of
So I pick any point in the codomain.
right,
It is not necessary that it has a pre-image, right?
right,
But if the map is onto, I know the range is equal to the codomain, right?
right.
So I pick any point y in y. There is going to be some point in x that gets mapped to this y, right?
Yes, ma'am.
Yeah, because it's onto, every point in the codomain is going to have a pre-image, right? So for every y in y, the codomain, there is a pre-image. Where will the pre-image lie? Domain or
In the
codomain?
codomain set.
In the domain?
Pre-image will be in domain,
Domain.
right?
Yes, ma'am.
This is pre-images. These are the images. Fine.
It can have one or more pre-images, ma'am.
Yeah, that is okay. But it should have at least one pre-image.
Yes, yes.
There is at least. Okay, I'll mention that. There is at least one pre-image. So for every y in y, there exists at least one x in x such that t of x is equal to y. Only then x is a pre-image for y, right? If t of x is y.
Madam, in this case, range will be codomain. Is it?
Range means you're looking at all outputs.
Yes.
It will be equal to the codomain means what? Every element in the codomain is an output of some input, right?
Yes, yes, yes.
Yeah. So is this statement clear?
Yes, ma'am.
So that's exactly what a onto linear transformation is also going to look like. For every w in w, the codomain, there exists a v in v such that t of v is equal to w. Agreed?
So every image is going to have a pre-image in the domain.
Every point in the codomain. Is an image of some point. That's what I want to tell.
Right.
So every point of the domain is an output for some input. Fine?
Ma'am, to say it simpler, one to many.
No, not necessarily many. It can be a one-to-one map also. No
Okay.
problem. Suppose this is my set 1, 2, 3 and this is my set say 1, 2. 1, 2, 3, 1, 2.
1 to 1, 2 to 2, and 3 it should be anything.
Is this an onto map?
Yes, yes, ma'am.
Yes, ma'am.
Why is
Yeah.
it onto?
Because
Because every
Because
every
every point
images
in
have the image.
yes, ma'am.
yeah, every point is
You will
having
look at every point in the codomain. Does it have a pre-image? Yes.
Yeah.
Yes.
Okay. Okay.
Is this an onto map?
no.
No.
No,
There is
because
some
2 left
point.
out.
There is some point in the codomain which does not have a pre-image. Agree?
Yes,
Ma'am,
ma'am.
ma'am,
But
here
then in case
if
if 3 is left out is fine, right?
No, then it is not even a function. No, function means every point in the domain should have some output, right?
Right.
This is
That
not
case
even a
will-
function.
Yeah, that will not qualify.
Yeah.
but if 3 is connected to 1 and 2 both,
No, then also it is not a function. No, every
uh,
element should have a
yeah,
unique
ma'am,
output.
it's not a function. But what about that linear transformation?
No, a linear transformation is basically a function.
Oh, okay, okay.
Is this a
Output has to be
one-to-one
one,
map?
input could be any.
Oh, sorry, can you please repeat that?
Output has to be one. A unique output has to be one.
No. Yeah. For a particular input, the output has to be unique in the sense that 3 cannot go to 2 different values. Then one of you will choose this path, another person will choose this path. There's ambiguity, right?
Right.
Then it is not a function.
And there has to be 0 in both sides or not?
Yeah. I'm just talking about a general function. Here I'm not talking about linear transformation. This is my set.
Okay.
This is my domain. This is my codomain. Is this map 1-to-1?
No, not one.
No, ma'am.
No.
No, ma'am.
No.
Is this onto?
Yes.
Yeah. Is this 1-to-1?
No,
Yes,
this
ma'am.
is- this
Yes,
is
ma'am.
not
This
a-
is not even a function.
This is not even a
Okay.
function.
So can you see that if there are more elements in the domain, the function cannot be 1-to-1?
Yes.
Yes, ma'am.
Yeah. Okay, so
So
we'll
it
talk
can be
about
R3 to R2.
So now I can think of this as R3 to R2.
Right.
Can it be 1-to-1?
No.
No, ma'am.
There are too many
No,
elements
madam.
here. I have to map everything into this set. So it cannot be 1-to-1, right?
Right.
But what about the other way around? R2 to R3. Can this be 1-to-1?
It can be.
Yeah. I'm not forcing any element onto this space.
Right.
But can it be onto?
No, ma'am.
No.
No, ma'am.
No, ma'am.
No.
Because there are
No,
too
ma'am.
many elements here. How will I go and find pre-images for everything in R2 in a smaller set, right? Say if I had 3 and 4, and 1 is going to 4, 2 is going to 1, 3 is going to 2. There's definitely going to be one element that's left out, right?
Left out. Yes, ma'am.
Because I cannot send one element to 2 elements.
Yes.
So when the codomain set is bigger, it cannot be onto. When the domain set is bigger, it cannot be 1-to-1. Fine. Bigger in the sense that when it's sets, we talk about cardinality. When it is vector spaces, we talk about
And can you
dimension.
just mention in your PDF that R3 to R2 can only be?
I will do that. This because I'm talking about sets, I'm not. Okay, let me write it here.
You
Cannot
can
be.
revise that while revising.
Yeah. Cannot be what? This cannot be smaller set. So 1-to-1.
1-to-1.
And this one cannot be onto. Okay, fine. So let's check what is onto. Let's go back to the same 3 linear transformations. T1, T2 and T3. T1 was this. How will I check whether this linear transformation is onto?
By
I'll just take
using
a
rank
picture of
nullity
this so that I
theorem.
can write it. By rank nullity theorem you can do, but otherwise. Now we don't know what is rank nullity theorem.
So by taking an element from codomain, checking
Ah,
whether its
yeah.
preimage exists or not.
So let me pick R into R3 T1.
Here the dimension of codomain is 3.
Yeah, so
We need to check the dimension of range.
okay, fine. But how will you check what is the range? Okay, since you have mentioned range, I will write down what is range of a linear transformation. What is range of a linear transformation?
Dimension of image space.
No. Oh, okay. Oh, range. Fine. What is image of a linear transformation?
Set of all output values.
Yeah, it is the set of all outputs. It is the set of all T of V, right? Where V belongs to the domain. Agree?
Yes, ma'am.
Set of all outputs. Where does this lie?
Codomain?
Codomain.
Codomain.
Yeah, this lies in
Domain.
the codomain. Okay, since we have discussed this, is this a subspace?
Subspace of what?
Subspace of, you tell me what, will it be domain or codomain?
Codomain, ma'am.
Codomain.
It lies in the codomain, right? So is it a subspace of W?
Yes.
Yes, ma'am.
How will you prove?
Taking
We'll take two elements
First
of
of all, does 0 belong to the range?
Yes.
Yes, ma'am.
Why?
because 0
It
always
won't.
maps to 0. T
T
of
of
0
0 is 0.
Yes,
Always.
yes, ma'am. Always.
So 0 is always an output, right?
Yes, ma'am.
Okay. How will we check for other two conditions?
We'll take two elements in this range of T.
Okay. So let's call
T of V1.
W1. Okay, fine.
Okay,
T of V1.
okay, ma'am.
T of V1
And T of V2.
and T of V2 belongs to range.
And we need to check T of V1 plus T of V2.
So you see there'll be a confusion when you write this notation.
It's better to go for W1, W2.
Yeah.
Yes, ma'am.
So say W1 and W2 belong to the range of T. So what do we know?
T of V1 equal to W.
There is a V1
There is some V. Yes, ma'am.
such that T of V1 is equal to W1, and there is some V2 such that T of V2 is equal to W.
Yes, ma'am.
Fine. Then what should I prove?
T of V1 plus V2 equal to T of V1 plus
I have to prove W1 plus W2 belongs to the range, right?
Yes, ma'am.
Yes,
How will
ma'am.
I prove that? I need to find a pre-image for this, right? Can you find a pre-image?
Ma'am, can we say directly that T of V1 plus V2, it goes to T of V1 plus T of V2?
Yeah, that's all.
Is it by the definition of linear transformation, ma'am?
Yeah. It's because it's a linear transformation, we can do this.
Am I right, ma'am?
Yeah. So I have found a pre-image for W1 plus W2, right?
Yes,
ma'am.
T of means V1 plus V2 is the pre-image, which means W1 plus W2 belongs to the range, right?
Yes.
What about alpha W1? Does it belong to the range?
Yes, ma'am.
Yes, ma'am.
Can you give a pre-image?
Alpha
Yes, ma'am.
V1?
Alpha times T1.
Alpha V1. What is the image of this?
Alpha into T of V1.
Alpha into T of V1.
That is
Alpha
W1.
Yeah. So I have found a pre-image, right, for alpha W1. So alpha
Yes,
W1 is also an output. So it belongs to the range. So the range is a subspace of the codomain.
Codomain.
So you have domain, codomain, a linear transformation. You have the kernel here, and you have the image here, image or range, right? So you just keep this picture in mind. If the kernel is equal to the 0 vector, it is a one-to-one map. That is, if this inner circle shrinks to one point, it is a one-to-one map. If the inner circle here expands to the whole set, if the image is equal to W, then it is an onto map. Is it clear?
Yes, ma'am.
Yes.
Can you
Please
repeat, ma'am?
once, ma'am, please.
So is it clear that there is a small, if I consider this these two as eggs, then this is the yellow part of this egg and this is the yellow part of this egg, right?
Yes, ma'am.
The
Okay.
kernel lies inside the domain and the image or the range lies inside the codomain, right?
Yes, ma'am.
Yeah, so I've just
Yes,
drawn that. If the kernel is just this single point, then the circle is going to be missing, right?
Yes, ma'am.
In this case, will the map be one-to-one?
Yes.
Yeah, that's what the condition is, right? The
Yes,
kernel
ma'am.
is 0 if
Zero
and
vector.
only if the map is one-to-one. Yeah. And if this circle is missing, what do you know?
That is equal to yes.
Onto, ma'am.
Means onto.
The image is the
Image.
codomain, so it's on.
Codomain.
Fine. So we are actually interested in these smaller ellipses. Based on them, how big and how small they are, we tell whether the map is one-to-one and onto. Fine.
Yes, ma'am.
So let's check whether our T1, T2, T3 are one-to-one onto or not. So what was our T1? I'll just write it like this: x comma y comma z gets mapped to 3x,
3x,
comma 2x plus y comma
3z
3z minus 2y plus.
Yes,
So the question is this map onto? How will I check whether it is onto?
ma'am. This image is equal to R3.
You want to check whether range of T1 is equal to R3. That is, you pick any point in the codomain. For every W in W, you should find a pre-image. Agreed?
Yes, ma'am.
Yes, ma'am.
Such that T of V is equal to W. So pick any W in W. What is the W here? What is the V here?
X, Y, Z.
W is 3x plus 2x plus y.
No. W, I mean capital W.
Capital W is R3.
Both domain and codomain are R3, right?
Both are R3, yes.
Yeah. How will any point in R3 look like?
3 components.
3 components.
It's going to look like some ABC, right?
Yes, ma'am.
So you pick any ABC in R3, find a pre-image. If you can find a pre-image, it is onto. If you cannot find a pre-image, it is not onto. Agreed?
Yes, ma'am.
Yes, ma'am.
So how will I check whether it has a pre-image or not?
A by 3, like that we can check.
I need to find an x
reversing.
comma y comma z that gets mapped to this. Agree?
Yes, ma'am.
So what is T of x comma y comma z? 3x comma
2x plus y.
2x plus y comma 3z minus 2y plus x. I want to find
X, Y, Z.
whether for all ABC, I can find an XYZ satisfying this condition, right?
Yes, ma'am.
So I want to check whether I can solve this system of linear equations. Agreed?
So we need to express this in terms of we need to find the values of a comma b comma c in terms of x comma y comma z.
Yeah. You tell me what I should find here. Should I find XYZ or ABC?
XYZ.
ABC, we start with ABC. We pick any point in R3. So we start with ABC. We want to find XYZ. Can you see that we are solving a system of linear equations?
Right.
Yes, ma'am.
Yeah. So can I find a solution? X is equal to
X
a
is
by
equal to
3.
a by 3.
Y is equal to b minus 2x. So 2a by 3. Z is equal to 1 by 3 into c minus x plus 2y. 2b minus 4a by 3. Something. When we simplify, we'll get something. So have I found x, y, z?
Yeah, in terms of ABC.
Yeah. I just put t of this x, this y, and this z. I'm going to get ABC as the output. Agree?
So we'll write the solution.
Ma'am, I have a doubt. If we find like this, always we can find out the values of x, y, z in terms of ABC, no, ma'am?
For this map, yes. Because it's on to, right?
Yes, ma'am.
Ma'am, can you take an
Then
example
where
which
it
is not
fails,
on
ma'am?
to?
I will do. T2, T3 is remaining, no? One of them is not on to.
Oh,
Ma'am, if we can find out the value of XYZ in terms of ABC, then it's always be on 2.
Because for any ABC, you are finding an XYZ satisfying this condition, right?
Okay.
Then it is on to, right? For any ABC, you're finding a pre-image, right?
Ma'am, can we say that if it is from R3 to R3, always it is possible?
No. Even then
No?
it is not possible. I'll give you an example.
Yeah, that's where my doubt is. Yes, ma'am.
Ma'am, if the dimension of that range is 2, let's take, then it won't be on 2.
Yeah,
If you
because
just remove this z in the, that 3z minus 2y plus x is equal to c, then it won't be the onto function.
okay, in this case, if I just remove, it won't be, but it's not always the case.
Oh, okay. So can you take an example of that?
Yeah, I will. Let's first deal with our T1, T2, T3, then I will do more examples. So T2 was from R3 to R2. This is the earlier map that we discussed. So T1, we already showed it is 1 to 1, right?
Yes,
ma'am.
And now it is on to also. T2 of x comma y comma z is equal to x plus y comma y minus z. Now, is this map onto? Is what I want to check. We showed that this is not 1 to 1. Now I want to check if this is onto. What will I do?
We'll start with
We
W1
start
comma
with comma z equal to a comma b.
I'll start with any a comma b in R2, and then I want to find x comma y comma z in R3, satisfying what?
T2 of x comma y comma z is equal to a comma b.
Right. I want to find a pre-image for this point. So what is T2 of x comma y comma z?
X plus y.
Y minus z.
Comma y minus z is equal to AB. Can I solve this system of equations? If yes, then it is on to. If no, it is not on to.
We won't be able to solve it.
Why?
Because we have got 3 variables here equating to 2 outputs, right?
What is the image of
We
a
need
comma
one more
0
equation.
comma minus b? What is the image of this?
The
0 will go to 0.
it's AB, ma'am.
A and B.
It's A comma B.
A comma
A
B.
comma
A
B.
comma B.
I have found a pre-image, right?
Okay.
I just want to solve, right? I don't want to solve it uniquely.
Only
I
when
just
it
want to
is
know
y.
whether it is solution.
Only when one of the thing is 0, right?
So what? I can solve this system, right? Not just this. What is T of a plus 1, comma, a plus 1, comma, minus 1, comma, b minus 1 or minus b plus 1. Right, minus b plus 1. What is the image of this?
X plus y is A.
A comma
Y
A
minus.
comma
It's A comma B, ma'am.
A comma B.
Right? I have
Y
found one more
minus Z. Ma'am, Y should be +1 maybe.
Plus.
Oh, y minus z should be
Yes,
equal
ma'am.
to
Y here Y should be +1.
no, y has to be -1 because I'm adding 1 here.
Okay.
No,
So that
A
means
minus
here
1.
A minus B
A
minus
minus
1.
1 and 1.
So let's fix
Should be
this.
minus b
Minus B minus
minus
1.
Z should be minus b minus 1. Okay, fine.
No, if you take A minus 1, that's okay.
Now is it correct?
Yes, ma'am.
Yeah, we can take A minus 1, 1 minus b plus 1. In this case also my output is A comma b, right?
So in this case of x plus y, if you subtract, you mean to say the same rule will apply and y will get cancelled. So we'll have x and
My aim is to find one pre-image. I have given you more than one, right?
Right.
There's nothing special about A and B. Whatever A and B I choose, I can do this, right? So is it on to?
Yes, ma'am.
So T1 was 1-to-1 and on to. T2 is not 1-to-1, but it is on to. Okay, what was T3? T3 was the other way around. R2 to R3 and T3 of x comma y was x comma y plus x comma 2y minus x. Can this be on to? Smaller set to bigger set. Can it be on to?
No, ma'am. You don't.
No, ma'am.
It was 1-to-1. Let's check whether it is on to. So if it is on to, I pick any ABC in R3. It should satisfy. I should be able to find T of x comma y satisfying this condition, right? X should be equal to A. Y plus x should be equal to B. 2y minus x should be equal to C, right?
Yes, ma'am.
So x is equal to A means what should y be?
B minus A.
Okay. So what is 2 times B minus A minus A?
2B minus 3A.
2B minus 3A should be equal to C. I cannot put condition on C, right? Can I put a condition on C?
You cannot find uniquely, right, ma'am?
No, it's not about uniqueness. I'm getting a condition in terms of ABC. That's not okay, right? ABC is any random thing.
They are kind of we are free to choose ABC. We can have condition
So
also.
what does this say? When will this system have a solution? Only when this condition is satisfied, right? Otherwise, this system doesn't have a solution, no?
Yes.
Because I'm getting the value of x from here, I'm getting the value of y from here, and when I plug that in here, it should be equal to C, right?
Right.
Only then the system has a solution. But when I plug those two values in here, I'm getting C is equal to 2B minus 3A. I cannot force C to be equal to 2B minus 3A, right?
So they're free to choose C.
Yeah. Say I take 0, 0, 1. Does this have a solution? Does this have a pre-image?
No.
What do I get? X is equal to 0. Y plus x is equal to 0. 2y minus x is equal to 1. When I solve these two, I get x is equal to 0, y is
Both
equal
are
to 0.
zeros. Yes, ma'am.
But when I put that in here, I'm not getting that it satisfies the equation, right?
Yes, ma'am.
Only when C is equal to 2B minus 3A, it is going to have a solution, right?
Restricting the codomain, ma'am.
Will this have a solution? Will this have a pre-image?
Yes, ma'am.
Why?
If we substitute, we will get it. No, ma'am. X is equal to 1, y is equal to 1.
When you, the C is equal to 2B minus 3A, right?
Yeah. So 2 minus 3 is minus 1.
Yeah. So only for A
Under
comma
this
B
condition.
comma C satisfying this condition, you will have a pre-image.
Yes, ma'am.
If it does not satisfy, you won't have a pre-image. So is this map on to?
No.
No.
So we have an example where it is both 1-to-1 and on to. We have an example where it is not 1 to 1 but onto. We have an example where it is 1 to 1 but not onto. Fine. We are left only with one case where it is neither 1 to 1 nor onto. We'll see that example also. But before that, let's find out the range of the linear transformation. How will you find out the range of a linear transformation? What is the range of a linear transformation?
All the
Set
outputs.
of all
images.
Output, yeah, the set of all outputs. So you are going to look at the set of all t comma v, where v belongs to the domain. Now tell me, what is range of t1?
Ma'am, we need to write 3x as a capital X and 2x plus y
No,
as
you
a
just look at
capital
it
Y.
and tell we have already done some calculation. Now tell me, what is range of t1?
Whole codomain.
We have shown that it is an onto map, right?
So it's R3.
R3.
Yeah. What is the range of t2?
R2.
R2.
So range of t1 is R3. Range of t2 is R2. What is range of t3?
It is not R3. Because it's not
What we know it is not R3. And I know that it is a subspace as well, right?
Yes, ma'am.
Yeah. So
Yes,
let's
ma'am.
find out what is range of R3. So how will I find out? The set of all x comma y satisfying t of x comma y is equal to, what? It is the set of all t of x comma y, where x comma y belongs to R2. Agreed?
Yes, ma'am.
R2 to R3, right. So what is t of x comma y?
X,
X,
y plus x.
2y
2y minus x.
Such that x comma y belongs to R2 means I can write it as x comma y belongs to R, right? Instead of the ordered pair, I am writing it as numbers. Agree?
Yes, ma'am.
Can you give me a basis for this subspace?
1.
1, 1, minus 1.
Minus 1.
0, 1,
0,
2.
1, 2.
What is the dimension?
2.
2, ma'am.
Yeah.
2, ma'am.
Dimension of range of R3 is equal to 2. And what is that called?
Dimension of image space.
Rank of the linear transformation. RANK. We denote it by RK of T. The dimension of the range is called the rank of the linear transformation. What was nullity?
Dimension of kernel.
Yeah. So you have the two eggs and the two yolks. Kernel image. This is nullity. The dimension is nullity. And this one's dimension is rank. And what is the rank nullity theorem?
Rank plus nullity is equal to dimension.
Domain.
Dimension of what?
Dimension of the vector space V.
That is
domain.
Domain.
Yes, ma'am.
So this is the rank nullity theorem.
Ma'am, why is it that the dimension of the range is equal to the rank of the linear transformation?
That's how it is defined. Rank of a linear transformation is the dimension of the range. Do you know rank of a linear transformation even before this? No, right? This is
No,
how it's
ma'am.
defined.
No, ma'am.
That's the
Okay,
definition.
so it's a definition. Okay.
Excuse me, ma'am.
Yeah.
Ma'am, for this basis, we are taking 1 and 0, x and y, correct, ma'am? Here.
Yeah.
Why we are restricted into 1 and 0, ma'am? Can we take some other numbers also?
You can actually take any numbers. You will get a spanning set. We are making it linearly independent by choosing that 1 and 0, so that you directly get a basis.
Okay, okay, ma'am.
Okay. So is it clear? Is it digestible?
Ma'am, even if we take that x and y outside, we'll be getting these elements, no, ma'am?
Yeah, but x and y outside. Now I can also do this, right?
How, ma'am?
Oh, okay. This is not going to be a
No,
basis, but
I'm
this
not.
will be a spanning
No,
set, right?
I'm taking the x. I'm pulling the x outside, ma'am. Here, so that 1 minus 1. And if we take out that y, it will gives 0, 1, 2.
Yeah, agreed.
Is
Okay.
it not? You are writing like that, ma'am?
Yeah, we are writing like that only. But take, for example, I have x comma y comma 0. Okay. X plus y. Suppose I have this. I can also write this as, you are saying I'll write it like this, right?
1, 0, 1. Y plus y into 0, 1, 1.
0,
1, 1.
1, 1. But I can also write this as x by 2 times 2 comma
0, comma 2.
0 comma y2. I will keep it as 1 plus
okay.
y minus x by 2, is it? Y minus x by 2 times. No, you see how I'm trying to manipulate?
Yes, I understood.
You can write it in a different way where this set will not be linearly independent.
Yes, ma'am.
You'll get a third element as well.
Yes, ma'am.
Yeah. So when we are putting that 1 and 0, we are making sure the set is linearly independent so that we get a direct basis.
So just scroll back, ma'am. So here you fix that x value as 1 and 0, and based on that, you
we get a
for
basis.
that. Oh. Okay, ma'am. Understood.
So here we are taking two components, ma'am, 1 and 0 and 0 and 1 to find the
For
basis.
x, we'll put x is equal to 1, y is equal to 0.
0 and again x is
and
equal
we'll
to
put
0.
x is equal to 0 and y is equal to 1. Yeah.
Okay.
Ma'am, can I ask it out? We are checking 1, 2 is same as looking the W is spanning for R2.
This one's codomain is R3. You mean R3? T3 is
R3,
from
R3 or R3 or R3 or R2.
You're looking for, you're checking whether the range of R3 is equal to R3 or not.
Yes,
but we are showing that it is a two-dimensional subspace, right? So it cannot be R3.
I just asked whether the range R2 or R3 according to the question.
Yeah. It's based on what the codomain is. Is that what your question was?
Is the W just look W is spanning R3? Is it correct for checking on to?
What is W? This one, is it? Is this what you're calling as W?
No, x, y plus x, 2y minus 6. Is it spanning R2?
Not spanning. This is a subspace. You're checking with, no, by R2.
The codomain should be equal to range. That is why I asked.
R3, right? Codomain is R3.
Yes. R3.
Yeah. You're checking whether this subspace, I know that the range is always a subspace. You're checking whether the subspace is equal to the codomain, R3.
Yes.
But it is not, because I am giving a basis with two elements, right?
Yes. I just asked not about this question. I am asking about is it true while I am looking about the W is spanning R3 or R2 according to the question?
Can you please repeat that? I didn't understand.
Just take the first question, T1.
Okay.
Mm.
T1 is
Yeah.
R3 to R3.
Just we are looking for 1, 2.
Yeah.
By ABC equal to
we did it
is
earlier.
Is it same as the W 3x 2x plus y 3z minus 2y plus x spanning R3?
No, what is a spanning set?
Spanning, not spanning set, span.
Oh, span of this. No, even
Span
then.
of this is R3.
What is span of that? Span of, you will have numbers, right? You won't have x comma y comma z and all, right? Span of this. Span of 1 comma 1 comma minus 1, 0 comma 1 comma 2. This is span of this set, right?
Yes. Does it become R3 then?
Then it is on to.
On to.
If it is not, then no.
Okay. Okay, thank you.
Excuse me, ma'am.
Yeah.
Ma'am, it's sort of a silly doubt, but I'm wondering if there's a geometrical way to test if a linear transformation is one-to-one or not. Because in maths 1, we had learned that if a function passes the horizontal line test, then it is one-to-one. So in the context of linear transformations, is there anything like that?
So one thing, horizontal line test, that was because you can draw the map of the function, right?
Yes, ma'am.
But then here you cannot draw the linear transformation, right? Because if you want to draw the graph, it is an element in the domain cross its image, right? This is graph, right? Graph of a linear transformation. Means if my linear transformation is from R2 to R3. Where is T3? T3 is from R2 to R3, right?
Yes, ma'am.
So where will its graph lie? Okay, I think I'm asking too much of an advanced question. F from R to R. How will you draw the graph?
Number line.
A number line.
It's a number line.
You'll take the domain. You will draw the codomain as y-axis. And then you will draw some graph, no? How will you draw this graph?
Ma'am, I'm not sure, but sometime back you had shown the scaling of a square.
Yeah, okay. No, but you tell me for this. How will you draw the graph of this function? You will take an x. You will see what is f of x. And you will plot it, right?
Yes, ma'am.
Right? This is how you draw the graph,
Yes, ma'am,
right?
that's how it's done.
Okay. So now suppose my domain is R2 and the codomain is R. How will you draw the graph?
Three-dimensional.
You will take a point, you will find its image and plot this, right?
Yes, ma'am.
So you have an x component, you have a y component and the output, right?
Yes, ma'am.
So the graph is in R3, right?
Yes.
So the graph of f is going to be a subset of x cross y, Cartesian product, domain, codomain. Agreed? Domain, codomain. Domain, codomain. Agreed?
Ma'am, if it's going from R2 to R, why can't the RHS be x comma f of x?
No, R2, no. So
No,
you
ma'am,
have two
the R
components, no? X
component.
component and Y component.
Oh, that will also be R2. Yes.
R component is just one. It's one number. This is one number. This is one number, right? F of x comma y is one number because it is in R.
Yes, ma'am. Yes, ma'am.
That is one component. Now say, for example, my map is from R to R2. How will I draw the graph? You'll take a point and you will plot the image along with this, right?
Yes, ma'am.
Where does f of x lie? Where is f of x? In R or R2? So this is going to give me two components, right?
Yes.
So something like this, f1 of x, comma f2 of x. Again, the map is in R3, right? Graph is in R3. It is in R cross R2. That is R3, right? Can you draw graphs in R3 with hand? Means on the paper?
No, ma'am, it's 3-dimensional.
So imagine what will happen if the linear transformation is from R2 to R3. Where will the graph be?
Five-dimensional.
We don't even know how 5-dimensional spaces look like, let alone drawing a graph there. Right? So that test, no, the vertical line test, horizontal line test and all doesn't work here. It works only for functions from R to R. If the
only if it's graphable.
Means only if you can draw the graph, you can talk about vertical line test or horizontal line test.
Okay, ma'am, got it.
Yeah. Oh, the thing that I was drawing, there I had R2 to R2. So instead of drawing them together, I took two copies of them. This is domain, this is codomain. And I was seeing separately what is happening. Fine.
Ma'am, is the session over, ma'am?
Do you have some other?
Yes, ma'am, we have stat 2.
Yes, ma'am. Stats class.
We have only 2 sessions for week 6.
Ma'am, we are short of 1 session.
Ma'am, can you arrange one more session in between these two?
We have, today is what? Today is Tuesday. We have one on Thursday.
Yes.
That Thursday session itself is an extra session. Okay, anyway, what and all have we discussed? We have discussed rank nullity theorem and 1-1 on 2. So I'll just give one example. I'll finish with one example which is neither 1-to-1 nor on 2.
Okay.
And then we have to do matrix of a linear transformation, right? Yeah, matrix of a linear transformation is left. Okay.
Kernel and basis of image.
We found no basis for range, basis for kernel. Here we did no. Oh yeah, there are other methods to do it. Yeah. Okay, we do that as well. So T of x comma y.
Can we put these two things which are left in the next session?
Yeah. I'll just give one example where the transformation is neither 1-to-1 nor on 2.
Okay.
What do I want now? I don't want a 1-to-1 map. So okay. So what about this map? How will I check whether it is 1-to-1?
Equated to 0, ma'am.
T of v is equal to 0 implies v is equal to 0. This is what I have to check. Otherwise, I will find the kernel, right?
Right.
It's a set of all pre-images of 0. I'll find this. Okay. So let's find the kernel. So I'm looking at the set of all x comma y that get mapped to 0. Oh, wait, it is getting mapped to 0. What about this map? X comma y such that x plus y is equal to 0, x minus y is equal. Oh, again, wait, I'm doing something wrong. What am I doing wrong? Oh, I'm making the map not on to. I need to increase the rank.
Ma'am, you can also take some example R2 to R2 where T of xy goes to 0, 0.
Yeah, or we can put T of xy goes to x comma 0.
Ma'am,
That's very
add
simple.
a scalar
Okay.
there. I believe a scalar will work.
Then it will not be linear transformation.
Yeah, we can do this example. X comma y to x comma 0 will also be neither on to nor 1 1.
Okay, this looks complicated, but it is simple. Okay, let's do this. X plus y is equal to 0, 2x plus 2y is equal to 0, minus x minus y is equal to 0. So what do we get from here? All three equations are the same, right?
Yes, ma'am.
Yeah. So we get x is equal to minus y from everything. Agree?
Yes.
So is this map 1 to 1?
No, ma'am.
No. Why not?
Because if we put the value 1 1, it will map to 1 comma minus 1.
No. What T of 1 1?
So yeah.
T of 1 comma minus 1. 0 0 0, right?
T of 2 comma minus 2 is also 0 comma 0 comma 0.
Yeah.
Yes, ma'am. T of 0 also 0 comma 0 comma 0.
So we have two different numbers that go to the same vector.
Yes, ma'am.
So it is not 1 to 1. The kernel is not 0. So it is not 1 to 1. Basis for kernel 1 comma minus 1. Fine. So what is nullity? One. Dimension of kernel 1. So what is rank? 1.
1.
Why 1?
Rank because dimension of domain is 2
minus nullity. Domain is R2. 2 minus 1 1. Can the map be on 2?
No, ma'am.
No. Why not?
No, ma'am, never.
Because rank is not equal to dimension of V.
Because there would be some examples wherein we cannot map that particular 0 to that any element.
Okay. But it is not on 2 because if it is on 2, then range is equal to codomain. Agree? So rank should be equal to 3, right? If it is on 2.
Right.
But that's not happening, no? We got rank is equal to 1, right?
Yes, ma'am.
Yes, ma'am. So it is not on 2. Can you tell me what is the range?
R3, ma'am.
No.
It's not on
If it is
2.
R3.
No, it's not on 2.
It is not on 2. If it is R3, then it is on 2.
Range is set of all
the images.
Ma'am, range is the spanning set of the basis 1, 2, minus 1 and 1.
No, that's all. Rank is 1. Basis has only one element. So you're looking for all those A, B, C such that T of x comma y comma z is equal to A, B, C, right?
Yes, ma'am.
Set of all A, B, C such that x plus y, I'll directly write x plus y is equal to A, 2x plus 2y is equal
Ma'am,
to
x
B.
comma y only, no, ma'am. It's R2 to R3.
Oh, is it R2? No, but range is inside R3, no? Oh, here. Okay, fine.
The x comma y. Yes, ma'am.
Minus x minus y is equal to C. From this, what can you tell? When will this system have a solution?
When
What about the
zeros,
first and
ma'am?
last? No. Why should it
No
be zero?
solution.
Why? What happened? Why no solution?
Ma'am, zero.
Ma'am,
When all are equal, ma'am?
when A is
Zero.
equal to minus C.
A is equal to minus C. What can you tell about the second equation? First and second equations.
A is equal to 2B.
Right. Agree?
Yes, ma'am.
When A is minus C and B is A by 2, this system has a solution, right? Agreed?
Yes, ma'am.
So that is range, right? Agreed?
Yes, ma'am.
Rank is 1. We already proved rank has to be 1, no? Here, using rationality theorem. So this map is neither 1 to 1 nor onto. Okay, I guess we'll stop here. We'll continue on Thursday.
Thank you, ma'am.
If anyone doesn't have a session and has doubts, you can ask.
Ma'am,
Yes,
We don't have any
scroll
doubt
back,
per
ma'am.
se. But
Scroll back.
Yes, ma'am. Just I want to take the photo of.
We'll upload this immediately after the session.
Then it's okay. Then I'll leave my house that session.
Yeah.
Thank you.
ma'am, can I ask?
Please.
Okay,
thank you,
this
ma'am.
session, like I believe we have completed all the theory concepts. So in the next session, we will be discussing only examples or 1 or 2 theory concepts left.
Yeah, matrix of a linear transformation. And then what else is there?
Ma'am, can you please give some example of metric representation of linear transform, because of this we are not able to proceed in the further video in week 6 or so.
Okay. So how will you find matrix of a linear transformation? So to write down the matrix of a linear transformation, the question of with respect to what basis comes into picture. So you should have a basis for the domain, a basis for the codomain, and only then you can write down the matrix of a linear transformation. Okay. So say I have this linear transformation. If I ask you to, you cannot do that. With respect to what basis that comes into the picture. So say with respect to 1, 1, 0, 1 for the domain. What is the domain for this linear transformation?
R2, ma'am.
R2.
Codomain?
R2.
R2 also.
Yeah, both are R2, but I'm giving different basis with respect to this for the domain and this for the codomain. Then what you will do is, you will first find out the images of the given basis vectors for the domain. You have a basis for the domain, take those vectors, find their images. What is T of 1, 1?
2, 1.
2, 1.
What is T of 0, 1?
1, 0.
Right. So can you, now you have elements in R2, elements in the codomain, express these in terms of the basis for the codomain. Can you express any element in the codomain as a base, as a linear combination of the elements of the basis for the codomain?
Can you please repeat?
Can you express elements in V or in W, say T from V to W? Can you express elements of W in terms of basis for W?
Yes, ma'am.
Why?
2, like this 2 1 is a 2.
Yes, ma'am. You
Because
can.
a base is a spanning set, right? That's the answer.
You can take 1 0 as a basis.
No, it's given. I have given a basis. So I can write it as 2 times 1 0 plus 1 times 0 1, right?
Yes, ma'am. Yes.
Yes, ma'am.
And this one?
Ma'am, here you have written elements of W in terms of basis for W.
So this is an element in W, right? Codomain.
Okay.
1 times
1
1
time 1
0 plus 1 times 0
plus 0 time.
No,
Perfect.
plus 1.
Why 1 time? 1 comma 0, no?
Right, 1 0.
I will write it as alpha times 1 comma 0 plus beta times 0 comma 1 and solve for alpha beta, right?
Right.
Yes, ma'am.
So alpha becomes 1, beta becomes 0. So how will I write down the matrix of the linear transformation?
2 1 1 0.
2 1 where?
Column.
2 1 in the
first column.
You will write the coefficients of the first this as the first column. And this as the second column. Not as rows, as columns. Is it clear what matrix of a linear transformation is?
Yes, ma'am.
Now suppose I change the basis. Same linear transformation. T of x comma y is x plus y comma x with respect to 1 comma 1 comma 0 comma 1 for both domain and codomain. Then what will I do? What is the first step we have to do?
You have to put the values and find the values of the transform.
So what will I get?
T of 1 comma 1 will be 2 comma
Same,
1.
no, whatever we got earlier, same transformation.
2 comma 1 and 1 comma 0.
After this, what should I do?
Now we'll write the basis and put the coefficients and solve for the equation.
What is the base?
Alpha times 1 comma 1.
2 into 1.
No. Normal basis is different. Yeah. Okay. You were directly solving. Okay. Yeah. So what will alpha be? 2. And then this has to be minus 1.
Minus 1.
What about the second vector? 1 times this.
1 times of 1 comma 1 minus 1. Minus.
Yeah. So now what is the matrix of the linear transformation?
2 minus 1, 1 minus 1.
Right. So can you see that for the same linear transformation, when I change the basis, the matrix of the linear transformation also changes?
Yes.
Yeah. So whenever you're asked to write the matrix of a linear transformation, the first question is with respect to what basis? Because based on the basis, the matrix is also going to change. Fine?
Yes, ma'am.
Okay. So is this enough? With this, can you proceed and then we'll discuss in the next session?
Yes, ma'am. Yes,
yeah.
In the next session, if we have less of concepts, can we have more problems to solve so that we get a good practice of this week 6.
Yeah, by the next session, we are hoping that you would have already seen the activity questions. So obviously, you're going to have more and more doubts.
Yeah, we'll have doubts. The only thing is, the only concern here is if we can, for example, what we have seen in quiz 1, the complexity of the quiz 1 was more than mock, which was a rare case to see in the last few years, last few terms. So if we can match up to that complexity, if more complex or difficult problems are come, we can easily solve the easier ones, right?
No, actually, we make sure that one of them is difficult. Okay, like
Like the last